Using spatial data, you can model real-world systems and interactions. This might be so that you want to predict something in another area that you think has a similar spatial structure to an area you're looking at. Effective models need to distill the essence of a problem into something where that you can make good predictions, and should predict better than tumbling dice. There are, however, limits on how much complexity that you can measure using digital data. It's useful to remember the words of the statistician George Box, who said all models are wrong, but some are useful. It's a good maxim for analysts and tells you to be cautious how you approach your analysis, but perhaps more so how you interpret the results of those analyses. Garbage in, garbage out is another useful expression to remember, because of course the results that we get are in a large part a result of the input data that we use in our analysis, and of course the selection of appropriate analytical techniques. Of course, many of the predictions we remember are the seemingly crazy ones that either did or didn't come true. So at the start of the 19th century, it was thought absurd that trains would ever travel as fast as stagecoaches. In 1943, the chairman of IBM thought that there might be a world market for maybe 5 computers. And more recently, in the year that the first iPhone was released, the then CEO of Microsoft suggested that there was no chance that they would get any significant share of the market. But predictions are used for so many things, from business modelling to the spread of infectious diseases, modelling climate change, and of course the possible effects of those changes. One example of predictive modelling for spatial interaction is the use of gravity models to estimate the flow of people, materials, or information between locations. They consider the attractiveness of a place, so some kind of measure as to why you would want to go to those locations. Then also the cost of the travel. That might be financial cost or the time cost. And these are then used to calculate the proportion of demand at each facility location. Such analysis could be used, for example, to calculate need, such as the amount of healthcare that would be required to satisfy demand. This would be based on the known ailments that affect different demographics, and of course using the demographic profile of your area of interest. Regression analysis can also be used to better understand the factors behind spatial patterns. So for example, you might identify spatial patterns in a population that are more likely to consume larger quantities of fast food. Might you be able to better explain and predict patterns of obesity or even stage 2 diabetes? These sorts of analysis could be used to target health promotion campaigns and better distribute healthcare resources. But please remember though, there's a big difference between correlation and cause. Don't fall into that trap. Correlation is a statistical measure expressed as a number that determines the size and direction of a relationship between 2 or more variables. Causation indicates that one event is the result of the occurrence of the other event, that there's a causal relationship between those 2 events. At a practical level, you might use regression analysis to try to understand one variable and then either predict from that variable for other information or model relationships between variables and test hypotheses. Regression methods attempt to determine the strength of a relationship between one variable, called the dependent variable, and one or more changing variables, known as independent variables. The relationship between 2 variables can be visualized using a scatter plot. Coefficients computed through regression show the relationship between explanatory variables and the dependent variable. Any portion that isn't explained by the model is shown by the residuals, that can also be a useful descriptor. Statistical analysis often requires that certain assumptions are met for valid conclusions to be drawn from that analysis. Using GIS, we're thinking and analysing spatially, so this often means that we have to pay careful attention to check that our data meets those required assumptions. For example, spatial autocorrelation is a problem for classical statistical tests, such as ANOVA, correlation and regression, because these methods assume independently distributed errors. You'll remember we talked about testing for spatial autocorrelation last week. So with that knowledge, you can consider if you have it in your data and how you can possibly deal with it for your analysis. As the analyst, you're the expert. Interpret your results carefully. You should have a good knowledge or at least an understanding of what you expect to see from your results. So carefully check your analysis if your conclusions differ significantly from what you would expect to see. Spatial data analysis involves a range of statistical and mathematical models. The techniques you use and the data analysis that we can use cut across a number of different disciplines. So learning to look outside your own discipline could help you find different methods that will help you with your analysis.